In the previous video, we've tried to decode anonymized features and guess their types. In fact, we want to do more. We want to generate new features and to find insights in the data. And in this lesson, we will talk about various visualizations that can help us with it. We will first see what plots we can draw to explore individual features, and then we will get to exploration of feature relations. We will explore pairs first, and then we'll try to find feature groups in a dataset. First, there is no recipe how you find interesting things in the data. You should just spend some time looking closely at the data table, printing it and examining. If we found something interesting, we then can take a closer look. So EDA is kind of an art, but we have a bunch of tools for it, which we'll discuss right now. The first, we can build histograms. Histograms split feature range into bins and show how many points fall into each bin. Note that histograms may be misleading in some cases, so try to vary its number of bins when using it. Also note that it aggregates the data, so we cannot see, for example, if all the values are unique or there are a lot of repeated values. Let's see another example. The first thing that I want to illustrate here is that histograms can confuse. Looking at this histogram, we could probably think that there are a lot of zero values in this feature. But in fact, if we take logarithm of the values and build histogram again, we'll clearly see that distribution is not degenerate and there are many more distinct values than one. So my point is, never make a conclusion based on a single plot. If you have a hypothesis, try to make several different plots to prove it. The second interesting thing here is that peak. What is it? It turns out that the peak is located exactly at the mean value of this feature. Seems like organizers filled the missing values with the mean values for us. So now we understand that values were originally missing. How can we use this information? We can replace the missing values we found with not numbers, nonce again. For example, XGBoost has a special algorithm that can fill missing values on its own, so maybe XGBoost will benefit from explicit missing values. Or we can fill the missing values with something other than feature mean, for example with minus 999. Or we can generate a new feature which will indicate that the value was missing. This can be particularly useful for linear models. We can also build a plot where on x-axis we have row index and on y-axis we have feature values. It is convenient not to connect points with line segments but only draw them with circles. Now, if we observe horizontal lines on this kind of plot, we understand there are a lot of repeated values in this feature. Also note the randomness over the indices. That is, we see some horizontal patterns but no vertical ones. It means that the data is properly shuffled. We can also color code the points according to their labels. Here we see that the feature is quite good, as it presumably gives a nice class separation. And also we clearly see that the data is not shuffled here. It is in fact sorted by class label. It is useful to examine statistics with pandas describe function. You can see examples of its output on the screenshot. It gives you information about mean, standard deviation, and several percentiles of the feature distribution. Of course, you can manually compute those statistics. In pandas, NumPy, you can find functions named by statistics they compute. Mean for mean value, var for variance, and so on, but it's really convenient to have them all in once. And finally, as we already discussed in the previous video, there is value counts function to examine the number of occurrences of distinct feature values. And a function is null, which helps to find missing values in the data. For example, you can visualize null patterns in the data as on the picture you see. So here's the full list of functions we've discussed. Make sure you remember each of them. To this end, we've discussed visualizations for individual features. And now let's get to the next topic of our discussion, exploration of feature relations. It turns out that sometimes it's hard to make conclusions looking at one feature at a time. So let's look at the pairs. The best tool here is a scatter plot. With it, we can draw one sequence of values versus another one. And usually we plot one feature versus another feature. So each point on the figure corresponds to an object with the feature values shown by points position. If it's a classification task, it's convenient to color code the points with their labels, like on this picture. The color indicates the class of the object. For regression, the heat map-like coloring can be used too. Or alternatively, the target value can be visualized by point size. We can effectively use scatter plots to check if the data distribution in the train and test sets are the same. In this example, the red points correspond to class 0 and the blue points to class 1. And on top of red and blue points, we see gray points. They correspond to test set. We don't have labels for the test set, that is why they are gray. And we clearly see that the red points are mixed with part of gray ones, and that is good actually, but other gray points are located in the region where we don't have any training data, and that is bad. If you see some kind of discrepancy between colored and gray points distribution, you should probably stop and think if you are doing it right. It can be just a bug in the code, or it can be a completely overfitted feature, or something else, but it's for sure not healthy. Now take a look at this scatter plot. Say we plot feature x1 versus feature x2. What can we say about their relation? The right answer is x2 is less or equal than 1 minus x1. Just realize that the equation for the diagonal line is x1 plus x2 equals 1, and for all the points below the line, x2 is less or equal than 1 minus x1. So, suppose we found this relation between two features. How do we use this fact? Of course, it depends, but at least there are some obvious features to generate. For tree-based models, we can create a new features, like the difference or ratio between x1 and x2. Now take a look at this scatter plot. It's hard to say what is the true relation between the features, but after all, our goal is not to decode the data here, but to generate new features and get a better score. And this plot gives us an idea how to generate the features out of these two features. We see several triangles on the picture, so we could probably make a feature to which triangle a given point belongs, and hope that this feature will help. When you have a small number of features, you can plot all the pairwise scatter plots at once using scatter matrix function from pandas. It's pretty handy. It's also nice to have histogram and scatter plot before the eyes at the same time, as scatter plot gives you very weak information about densities, while histograms do not show feature interactions. We can also compute some kind of distance between the columns of our feature table and store them into a matrix of size number of features by number of features. For example, we can compute correlation between the columns. It's the most common type of matrices people build, correlation metric. But we can compute other things than correlation. For example, how many times one feature is larger than the other? I mean, how many rows are there such that the value of the first feature is larger than the value of the second one? Or another example, we can compute how many distinct combinations two features have in the dataset. With such custom functions, we should build the matrix manually, and we can use matShow function from matplotlib to visualize it, like on the slide you see. If the matrix looks like a total mess, like in here, we can run some kind of clustering, like k-means clustering on the rows and columns of this matrix and reorder the features. This one looks better, isn't it? We actually came to the last topic of our discussion, feature groups. And it's what we see here. There are groups of very similar features, and usually it's a good idea to generate new features based on the groups. Again, it depends, but maybe some statistics calculated over the group will work fine as features. Another nice visualization that helps to find feature groups is the following. We calculate statistics of each feature, for example, mean value, and then plot it against column index. This plot can look quite random if the columns are shuffled. So what if we sort the columns based on this statistic, feature mean in this case? It looks like it worked out. We clearly see the groups here. So now we can take a closer look to each group and use the imagination to generate new features. And here is a list of all the functions we've just discussed. Pause the video and check if you remember the examples we saw. So, finally, in this video, we were talking about the tools and functions that help us with data exploration. For example, to explore features one by one, we can use histograms, plots, and we can also examine statistics. To explore a relation between the features, the best tool is a scatter plot. Scatter matrix combines several scatter plots and histograms on one figure. Correlation plot is useful to understand how similar the features are, and if we reorder the columns and rows of the correlation matrix, we will probably find feature groups. And feature groups was the last topic we discussed in this lesson. We also saw a plot of sorted feature statistics and how it can reveal us feature groups. Well, of course, we discussed only a fraction of helpful plots there are. With practice, you will develop and find your own tools for the exploration.